Welcome to my talk on analyzing the FinCEN files with Neo4J. My name is Michael Hunger. I'm leading the developer relations team at Neo4J for many years. So this is a topic that I'm actually quite excited about because this is both recent, it's really important, it's an investigative use case, and it brings together graph analytics and graph databases with investigative reporting, which is really cool. In September, the International Consortium of Investigative Journalists launched a new investigation called the FinCEN files. And this is based on a data leak they obtained from the Financial Crimes Enforcement Network in the US Agency of the Treasury, where international banks have to report suspicious activities from money transfers to this agency. And the journalists did a really interesting job there, and we want to dive into this today. Neo4j itself has a long history of collaborating with the ICIJ. It already started early in 2014 with the Luxembourg leaks and the Swiss leaks, and the ICIJ has been using Neo4j for many years for the connection aspects of their investigations, kind of connecting the dots like in a detective investigation, basically. If you have all the pieces of the puzzle, but you don't see the connections, that doesn't help you. But as soon as you see how things and people and events are connected, then you can find out much more. So for the source reports or suspicious activity reports, those are mostly reported by banks or by compliance officers of banks when they see something like insider trading, money laundering transactions, transactions connected to well-known criminal figures, or kind of suspicious receivers or senders, money volume sometimes, and shell company related dealings and so on. And so they have to report this to the FinCEN and to the US Treasury within a certain data range, but often they actually don't do this. And interestingly, looking at the data or reading what the ICIJ said about the data that they got is that these reports are often very insufficient, basically, to make decisions. In the ICIJ investigations, they go really deep, and of course, they only use these data leaks as starting points for their investigations. So they basically do what every good journalist does. They take this kind of suspicion and take this data and turn it into a real local investigation that then kind of spans many journalists and then results in stories being reported. And what's interesting in the data that we can also see is that many global banks are actually involved in moving illicit money, which is quite impressive and scary in some form. So I think in some ways it's both kind of unknowingly, so the banks are kind of overwhelmed by the volume and complexity, and also the kind of setups that criminals put up to move money around, from multi-staging to splitting money flows to using lots of intermediaries and so on. So this kind of means that the anti-money laundering capacities of the banks is not sufficient as such that they have. What's actually concerning is that even if banks knew recipients of the money, they continue to move the money around even if those people are on sanctions lists or have certain other qualities or attributes that would kind of identify them as suspicious. And the ICIJ published a lot of stories with all their local partners around this, so you can read in all the global and local newspapers around this. And they also published a really nice data visualization here where you can trace these flows around the world, and also highlighted some of the notorious people in these reports. So definitely worth a read. I'll share the link again. Looking at the data, actually, because that's kind of what we want to look at, not the stories behind it. The original data was leaked to BuzzFeed, and those were mostly documents and PDFs and spreadsheets. Those leaked documents contain 2,100 filings, around $2 trillion, which is a staggering amount of money, but those represent only 0.02% of the total 12 million filings over the last 25 years or so. So it's a tiny fraction that was leaked, and this is already $2 trillion, which is really crazy. The ICIJ did a really long investigation this time with 80 journalists. The main reason for that was that they had to fact check these filings manually. They tried initially to use OCR and then machine learning tools to check entities that are part of these filings, but they were not so successful, so they had to do it manually. So they basically built inside of the ICIJ an AML tool, an anti-money laundering tool that banks could probably get from them, which is kind of fun. They, of course, also use their text analysis tool called DataShare, which is open source, to extract entities from the text, if possible, and kind of manage all the PDFs and documents. And Neo4j and Linkurious, our partner, were used for visualization and inspection. So they used the data from the spreadsheet, the data from the reports that was visible, and connected the dots as they did before. The ICJ also published some of the data as CSV files, but this is really minimal aggregate data. It's really just the filings, the money amount, and the banks that are involved. So all the underlying data, like about the entities, people, the detailed findings of the compliance officers of the banks, and so on, is not in there. We can take this published data and input into Neo4j and analyze it there. So that's what we want to do today, and I'll give you a demo as well about this. So that's what it would look like. On top here, you see the data model. So an entity is a bank, which is in a country, and the filing is one of these suspicious activity report filings, and that has different relationship types to the bank. So the entity could be originator for the filing. The filing could concern the bank. It could be the entity who filed the filing, kind of the reporting entity, or an entity that benefited from that. And I added an additional relationship between banks that indicated the money flow that basically aggregates all the filings between two banks into that. But we'll see this in a second. And then we can look at the data in Neo4j browser, Neo4J Bloom, and then use some graph data science. So some quick words about Neo4j. Neo4j itself was built to make sense of data and care about the relationships of the data. So it's a purpose-built graph database, which is meant to handle relationships and complex domain models, complex domains with a lot of interconnections, also a lot of dynamic interconnections between entities efficiently, so you can query, store, and manage this kind of data really efficiently, because it's kind of from the ground up a native graph database. And it's everything from social networks, network management, money transactions, purchase transaction networks, recommendations, knowledge graphs, and so on. So whenever you can think about something that you can draw on a whiteboard as circles and arrows in your domain, and many companies actually have complex domains. So right, if you're deep into it, then you know that you have lots of entities and lots of connections between them in your domain model or in your database model as such. And so graph databases are built, purpose-built for that. Okay, Neo4j is not just a database in the middle, but it's also comes with graph data science, graph analytics. We have a lot of like drivers and APIs on top of that. We have developer tooling, data integration tooling, and UIs for data analysts as well. So there's a lot of stuff around the core database, which is all going together into that. On the data model, it looks like this. So entities in Neo4j are called nodes. They can have arbitrary attributes. So the attributes are basically key value pairs. So you don't need to preset them. So you can add them at runtime. There's no schema as such, and which is really nice. And you can also label entities. So if you have types or tags or similar things that you want to put on entities, then you can put as many on an entity as you want. So you see here that I have two entities, two nodes that are called entity, which are the banks. And then you could add additional labels like sender and receiver or something like that on the bank. So if it has ever been a receiver or has ever been a sender, so some banks might have a receiver and a sender label on top. And in the middle, you see the filing. The staggering amount I put there as an example is actually in the range that that some of these filings really have, which is really billions of dollars. And then most important, of course, relationships connect nodes in a graph database, and relationships have a type and a direction, and they can have also additional arbitrary attributes on top of them. Those attributes and relationships often qualify the relationship as such. So graph data science is basically a part of data science which looks at the relationship in the data, which takes like information from knowledge and knowledge from topology. So not just looking at attributes of data like you would do traditionally, but you look also at how are the my data points connected, right? So are they kind of spatially close together? Are they temporally close together? Are they connected by an event? Are they connected by an other piece of information? And this kind of information is additionally used on top of that. For Neo4j, that means we have the core database, which integrates with a graph data science library, which brings along a lot of algorithms, and an in-memory analytics workspace, and Neo4j Bloom as a visual exploration tool. So we have algorithms around centralities, cluster detection, link prediction, and similarity. And now with the newest release that's going out soon, we also have things like embeddings, which is then really interesting for integration with machine learning tools as such. And basically what we do is we project from the graph store arbitrary shapes of data into the in-memory graph for the graph algorithms library, and then run the algorithms on that to kind of compute new information. It's kind of like an unsupervised algorithm which kind of uses this topological information to compute new kinds of data. Okay, and with that, I want to go into demo mode because that's what you've all been waiting for, and me as well. So let's see, I just exit the presentation real quick, and then we can get into it. 1 second, where's my browser? Desktop. Oh, I think I have to really exit the presentation. Okay, so what we start out with is Neo4j Sandbox. So you can go to sandbox.neo4j.com. You can run along if you want to. And in sandbox.neo4j.com, you can click on New Project. And then on the bottom left, you will find the ICIJ FinCEN files. I already started this, so you don't have to wait. And then you can open a Neo4j browser on top of the data. So this is the dataset already imported. If you want to know how to import the dataset and do more with this, I have a GitHub repository here which has all this information there, which I'll also share at the end again. Okay, so we have our sandbox here, and we can just say open with browser, which opens up our Neo4j browser. And here we see we have 7,000 entities, 43,000 relationships in the data, which are banks, filings, countries as well. So for instance, if I pull a bunch of entities, I can just click on this, then I see a number of banks here as such. But what's really cool about the sandbox is it comes with this kind of guide that kind of walks us through stuff. We can also watch a video from the ICIJ. So we can look at things here or in Neo4j Bloom, which I'll do in a second. Or actually, let's do this first. So Neo4j Bloom is an interactive non-developer tool for data analysis. So we can also from the sandbox here open Neo4j Bloom. And if we open that, we can then log into that. See, that's what we have to do. Here, I just copy the password. So these sandboxes are custom and disposable, so you can create your own. So everyone has their own sandbox. You can also modify the data there so you don't affect anyone else. So I'm connecting to this graph, and then you can see a quick investigation of the data shape. Let me start anew, and then I have an error here. Try to reload this. Okay, so now we can investigate the data. So for instance, if you just want to look at all the filings, that would be simple. But what I wanted to see is, for instance, if I have a filing which benefits an entity, which is a bank, right? And then this entity is in a country where the name of the country is Russia, for instance, right? So kind of money flowing to banks in Russia. So you see that it automatically takes my input and turns this into a graph pattern. So filing benefits entity with country Russia. And if I run this, then it pulls the data from the database and shows us the information visually, right? So the reddish ones are filings. The size of the filing I configured to represent the volume of data. So for instance, if I look at this one here, I see that this has a lot of money in there, like $2 billion or something like that. And the yellow one is the country, and then the purple ones are the banks. And if you scroll in, then you can also see the details of the banks and how much money was in these filings. All right. The other thing that I can do here is, if I clear the scene, I can also say, okay, how are banks related to each other? So which banks have sent money to each other? So I can say entity transferred entity, so which is kind of my inferred or projected network on top of the data. So I see basically clusters of banks running together. So click. And if I run this, I should see all my clusters of data. Let's see. So there's individual connections here, as you can see, right? And then there's larger clusters of banks that have sent money to each other, right? And the big main cluster. So I think most banks have been involved in one way or another in these money transfers. So that's why kind of the cluster in the middle contains all of them. Okay, to get into more data sciencey things, we can export data as we've already done here as well. So that's just sorting things by volume. The money flows, I talked already about the transferred relationship. So basically what I did here was I looked at a filing where one entity, one bank is an originator, another bank is the beneficiary, and I aggregated all the money on all these filings between these two, and then created a new relationship between the two banks and set the amount as a property on the relationship. So that's kind of a projected graph or inferred graph. And then I can use this actually to run graph algorithms, for instance, clustering algorithms, which allow me to say, okay, which entities go together. And to show you this, I could run the code, but actually I want to show you the tool that we built to make this easier for people to get started with. So it's called Graph Data Science Playground, and you can connect it to any Neo4j database, or run it locally with Neo4j desktop. And here you see I selected an entity which transferred with the transferred relationship and the amount property on the relationship, and then I can run a clustering, so in PageRank algorithm, so which kind of covers the transitive money flow, so from A to B to C. And if I run this, I get a result chart, I get an table, sorry, a chart visualization, and I can also get a visualization here. Let's see if this works. Yeah. So you see the size of the nodes is kind of according to their page rank. So how much money went to these banks as such. So Ross Bank is, for instance, one with a lot of money that went not just directly, but also indirectly there. The same we can do for clustering algorithms. So in this case, we have Louvain. So we can pick the same. So we have entity, transferred, and natural amount. And we want to store this under Louvain. And if we run this algorithm on the data, we get results back as well. And the visualization looks like this. So we can actually use PageRank for the size and Louvain for the color. And if we do this, we should have a more colorful representation, which has the the different clusters. So this is only a subset of these. So we can also pull this all into Bloom. So that's two parts where we can run traditional graph algorithms on the data. What I want to show you now is more of the new stuff. So we have a new release coming out soon of the graph data science library, which is then more focused on embeddings, basically, and nearest neighbor networks. So embeddings are but if you want to learn more about the data science, you can go to neo4j.com developer, and there's a whole data science section which also has conceptual explanations of graph embeddings and things like that. So that's really useful to learn more about this. So basically, embeddings are representations as vectors of certain facts, right? So for textual analysis in Node2Vec, an embedding represents the meaning of a word as an 128 to 1024 long double vector. And in a graph, an embedding captures the topology of the graph. So where does this node sit inside of this graph with regards to its neighbor? What kind of shape of neighborhood is this in? And it can also take attributes into account as such. And so in the library, there are now three embedding mechanisms: random projections, or fast RP, Node2Vec, and GraphStage, which are also in the preview documentation. So you can see these here in Graph Data Science 1.4 preview. And fast RP is the one that I want to use. So I basically take this data and try it out. Because the Sandbox doesn't have the latest version of the library here, I'll switch to my local environment, which is called Neo4j Desktop, and which also has a FinCEN database, which I just imported here from a dump file from the GitHub repository. And I installed the Graph Data Science library into that, as you can see here. So, and on here, I can also run my Neo4j browser. And with that, we can run these embeddings. So in the sake of time, I won't actually run all this stuff one by one. Or actually, I could graph drop, because it's actually quite fast. So what you can do is the following. I just sneak into my browser, because I have this stuff all in my presentation here. And so what we can do first is we create an projected graph, which takes the transferred relationship that I mentioned, and this time a participant label. So these are all the banks that actually have a transferred relationship, so I don't get empty ones or kind of lone nodes into that. And I have a normalized version of the amount, which is 0 to 1 normalized on the relationship. So I just run this, which creates an in-memory graph of the data, which goes really quickly. And then I can run my embedding algorithm on top of that. And the result of the embedding algorithm is 128 sized double vectors embeddings that I'll show you in a second for each node, which captures its topology and also the weight of the relationship as well. So here you see some banks and their embeddings, basically, right? So and you see that it's kind of representative. Basically, the embedding is not 0 and it's not kind of empty or something like that, but it has real numbers in there. And what's now interesting with these embeddings is that we actually want to not just write this back. So what I did here is I just wrote it back to the Neo4j graph. So it's now really a property on the node. But what I can also do, I can also add this to the in-memory graph. So I have the embedding in the in-memory graph as well. And then I can run an KNN similarity algorithm, which gives us a similarity network here as such. So basically, we can say on our transfers network, we want to run a top K KNN algorithm on the embedding, and then give us back the results. You could also write this to Neo4j then as similar relationships as well, which would also work. So, and here you see similarities between banks based on their embeddings, basically. So these embeddings can, of course, also be passed to traditional machine learning tools and workflows to be used later. Okay, and with that, let's go back to the last few slides of my presentation. So why is this whole thing important? Why do we do this? So I think adding graphs to the mix of your tool set, of your tools, gives you the ability to not just look at the attribute data or kind of matrices or rows of data, but also to look at connections. And this will help a lot in, identifying relevant entities in a network, kind of spotting certain patterns, and the integration of graph data science with traditional data science tools with the use of embeddings and metrics that are computed by graph algorithms actually improve the accuracy of ML models, which has already been proven, and will help to get better predictions as such. And for the investigation itself, I think it's really important that banks are getting better at their anti-money laundering, and the criminals should not be able to transfer money, especially not these volumes as such. If you want to learn more, you can check out the investigations from the ICIJ on their file on their website, or explore the data in Neo4j on the Neo4j Sandbox, and we've also written a blog post about this. And with that, I'll happy to take questions. Thank you.